Everybody, thanks for coming. It was a bigger turnout than I thought. It's in this new age of Teams meetings, it's nice to be in person again. So we appreciate you coming out. This team's very excited to share with you these findings that we've been studying for the last year. So this is a very diverse group. I wish the whole team was here. Only 4 of us are here today, but I'll get into that in a minute. But I want to you're going to handle the disclaimer? Okay, that's fine. So I want to introduce the team real quick. So first and foremost, I'm sorry, I wanted to walk away from the mic. Sorry, Jay. Introduce Alvin Johnson. He led this team, actually. He led it, put this all together, worked with the team, did an outstanding job leading this team through this for the last year. And he's representing the Nix water treatment team. So Alvin Johnson, thank you very much. Thanks. Next is James, representing from the lab, and we're very grateful to have James on the team. He, all that science we don't understand, we're not as smart as all of you in the lab. He helped us with the chemistry and understanding all the science behind it. Not only that, we wanted to make decisions, and you'll find this out here pretty soon, off facts and figures, not opinions. Hence the reason to do this study. And over a year, there was a lot of data. James, master in Excel, was able to take all this data and put it in a viewable picture that makes sense. And you'll see what wonderful work he did here in a minute, where you just look at one picture and it says everything. So thank you, James. Brandon, Mr. pH, eats, lives, breathes this right now out on water quality. Probably the one that's going to benefit the most out of this. Make your life a little bit easier. But one of our subject matter experts on the team brought a lot to the table. We couldn't have done it without you, so appreciate it. And then Mike Macklin. He's on military leave right now. Unfortunately, can't be here, but I think it's a pretty good reason to not be here representing our country. He was another subject matter expert, and he also represented distribution and SOS out there with all the stuff, and another subject matter expert. He also was our liaison between the manufacturers, did a lot of the liaison work between the manufacturers and Denver Water. So played a big part in there. Mike did a great job. Hopefully he's a senior tech here pretty soon. Then we had Stephanie. Stephanie came to us at the end, probably been with the team for about a month, a little over a month, maybe 2. Helped us write this report. So I'm going to go get it here in a minute, but it's 37 pages. So she helped us do the scientific report writing. So very beneficial to the team. So appreciate treatment letting us have her, or the SEO team, for a little bit. And last but not least, Craig. Craig started with the team when we started over a year ago, helped write the executive summary, getting this going, worked very hard on how probe selection was done, and played a big part in that. So then he had to leave for a while to get trained in treatment, and then he came back at the end to help us. But he's on vacation this week, so we missed him. So that's about it. I'll turn it over to you.
Excellent. Thank you. So we'll catch up on our slides here. All right, so I want to do special thanks. The treatment plants helped out tremendously in this, right? We couldn't have done it without them. They were the ones that had hands-on in doing the benchtop analyzing and doing that day-to-day work with the pH probes. So Marston, Moffitt, North and South operations team, thank you guys for helping us out. Throw out a special thanks out to Nicole Poncelet, Brian Good, Marcus Thomas, and Virginia Roberts. They really allowed us to get this study going and were the core support there for us. I also want to mention Jason Gerard. He built the panel originally and set all of the actual display up, and it built all of that. So all the physical work was done by Jason Gerard. Bill Wagner and Joe Burcham both did the programming between the North and the South systems. So special thanks out to those guys as well. And all the other people that helped us along the way with ERIS and other issues we had with reporting and stuff like that. Thanks for all the help. Okay, why we did this. Main reason, the increased pH, right? The lead reduction program raised our pH from the 7.5 it was to 8.5 to 9.1 was our range out in distribution. That created a lot of problems with the pH probes we currently have. The tighter tolerances that we had to get, the higher pH, made the current probe we have less responsive and a lot more maintenance. There was a lot of frustration with the operators. We were basically doing 4 times what the manufacturer said was required maintenance. We'd do 4 times that amount to keep the probe reading where it needed to be, where the operators would trust it. So that's one of the main reasons we started doing this study. Other reason was the pH probe that we mostly have at the treatment plants wasn't really designed for that tight of a tolerance. So we wanted to look for something, plus the technology changed over the times. So we picked a bunch of probes that were newer and hopefully the top. Other than that, we went through multiple vendors, kind of reached out to them, see if they would donate us a probe and what options we had for the newer technologies on pH measurement. This is a little slide about the lead reduction program. Since we've been doing the higher pH, we've had a drop of 70% in the lead levels. Most of those lead pipes, actually all the lead pipes, are all owners, like houses, spigots, all this stuff is all owned by homeowners, not Denver Water. But this is what we've got so far, is 70% reduction since we've been running the higher pH. Helps the corrosivity, geez, I can't even say that word. Corrosivity of the water. So that's where we're at with the lead reduction program at this point.
All right, and this is all the probes that participated in the study. We had 11 altogether. As Alvin mentioned, we reached out, and this is meant to be a snapshot of what we saw in the market at the time, which was about a year and a half ago. Lots of good variety here. Not only did we look at different pH probes, but we also looked at whether they were maintainable or replaceable. So can we replace specific parts in that probe, or when it dies, does it just need to be replaced altogether? We looked at technology that was involved in the probe. Is it a smart probe? Is it a brand new technology that hasn't been used before? Is it something that we're familiar with? We also looked in the user manual for operating specs. As you can see in that column there, lots of different specifications all across the board here. We also looked for recommended maintenance within that user manual as well. Ranges all across the board from no maintenance whatsoever to replace everything yourself or replace the probe, all across the spectrum. And lastly, we looked at the maintenance cost itself. As we estimated this to be about $68 per hour for maintenance and parts. And we'll get into that a little bit later as we start looking at figures, but we definitely wanted to include a maintenance piece in that as well. So the target state, ultimately what we were trying to do was evaluate all these probes and find the most suitable ones for Denver Water with regards to our source water and treatment processes. This is not a recommendation to buy specific probes over another. This is certainly just Denver Water's experience with these probes. Every single pH probe is manufactured differently, and they will respond to different processes in a different way. So, again, the purpose of the study was for Denver Water only, just so we can find out what works best for us, according to these 3 criteria that we have listed here. The first is to identify probes that have the least amount of inherent drift. What do we mean by drift? Over time, when you have a pH probe, as it runs and runs and runs, it slowly drifts down, and eventually it's going to reach a mark where it triggers maintenance being needed or replacement. So that drift down is really what we're referring to. The longer we can have it remain in our bandwidth, the better. So this is addressed specifically in the following results by the percent within limits, ultimately just a calculation that calculates how often the sensor was within our 0.1 SU bandwidth. I'm not going to get too far into the numbers here. James is going to handle that a lot better on. Number 2, we wanted to identify pH probes that are capable of precise and accurate measurements at the required pH. Precision and accuracy are even more critical now than ever, especially with the LRP. We have to maintain that pH within that bandwidth, and we have to have accurate and reliable and precise readings. So precision and accuracy are represented by relative standard deviation and accuracy respectively. And we also wanted to account for planned or unplanned maintenance in this as well. Because it doesn't really matter if we have a probe that works great, it's got no drift whatsoever, and it's precise and accurate, but every single week, for whatever reason, it just has to be calibrated. That's not going to do us any good. So we really wanted to account for maintenance as well. The main thing that I'm trying to thank you. The main point I want to drive home from this slide is that all values on the following charts and graphs are a direct response to the goals of the study. And once we look at the data, we will explain what the values mean a little bit more. Awesome. Thank you again. So what did we do? A lot. There are a lot of variables that could impact this study, and we really did our best to try to eliminate as many variables and uncertainty as possible so we can get the most accurate and reliable results. This is a well-researched and well-thought-out study with high-quality data. So, starting at the top, we did grab samples every 4 hours at specified taps at the treatment plants. That's 6 samples a day. We had 7 months of data at Marston and 3 months of data at Moffett. Lots of data to work with, huge sample size. The samples were rinsed to ensure accuracy and avoid interference from contamination. The grabs at the time that they were recorded, the online analyzer reading was taken as well. This online analyzer data point was used as a validation and verification to ensure grabs were accurate. Data was also invalidated and reviewed. So grabs were compared to the online analyzer data, and if the difference between those two values was greater than 0.2 SUs, then the data on 2 hours of either side was invalidated. To give you an idea of how much data was invalidated, not much. Our pH is looking really good. For 7 months at Marston, only 2 points were invalidated, and Moffett only had 3 months of data, yet it had 68 invalidations. The grab probe was calibrated once per shift with temperature chilled buffers. The data was also entered once per day to prevent data loss or operator error. The same sample guidelines and instructions were given to operators at Marston and Moffett. In addition, frequent spot checks were performed by the core team. So we stopped by the panel, looked at it, made sure flows were looking okay, everything was getting water, everything looked normal, there weren't any alarms. And we also checked SCADA frequently to make sure that everything was okay as well. We followed manufacturer recommendations for maintenance in addition to quarterly calibrations. And from the beginning, we have been open with manufacturers and representatives so that they were in the loop and aware of how their sensor was performing. We wanted no surprises when we got to the end of the study, so every manufacturer knows how their probe has been doing up until this point. Response time. We wanted less than 48 hours downtime, so the accuracy and percent within limits are as accurate and representative as possible. And lastly, this study took approximately 1,500 hours of manpower to complete. So it's well thought out, well researched, lots of effort went into this. Let's look at some data.
So this is a summary of the data we used to evaluate the performance of all the probes while they were at Marston. We assessed the probes based off of 3 criteria: relative standard deviation, percent within limits, and accuracy. Relative standard deviation is the spread of the data relative to the overall average, in this case, the average of the plant pH probe. It's represented as a percentage. The lower the percentage, the tighter the spread is relative to the average value. Percent within limits essentially is the percent that all of the probes were within Denver Water's required range. Finally, accuracy was determined by calculating the total percent of data points within plus or minus 0.1 SU of the benchtop probes. Each of the criteria had ranges with numeric values assigned to them. So based off of the where the probes landed within those ranges determined which value they received. Also, each of the criteria were weighed by applying a multiplier. Thank you. And then finally summing all the data. We concluded that the probes that were the best fit for Denver water were ECD, Mettler-Toledo, Rosemount, and Yokogawa. So the next 4 slides, we plotted each of the top probes against the plant pH probe. Along the x-axis, you have the time series. Along the y-axis, you have the pH. The dashed red line are Denver Water's upper and lower limits within the distribution system. The blue line, in this case, it's ECD. In the yellow line is the plant probe. We also plotted the moving average for the plant probe, just in order to get rid of the noise that you see with the raw data. The ECD probe trended very well with the plant probe. For the most part, it was slightly higher and then slightly lower towards the end of its time at Marston. It had an RSD of 0.65%. Basically, 99.9% of the time, it was within Denver Water's limits. It also had the highest accuracy at 97%. Also, there was no maintenance performed for this probe other than the routine calibrations that were performed for all the probes. So the Mettler-Toledo probe kind of struggled within the first couple of months, and then it started to consistently trend higher than the plant probe. We calibrated it in late August, and it trended very close to the plant probe. It had an RSD value of 0.94%. It also was 99.9% within Denver Water's limits. It had an accuracy of 88%, which was due to the performance of the probe prior to the calibration in August. It also required no maintenance other than the quarterly calibrations. So the Rosemount probe trended with Marston probe, benchtop probe for the majority of the test period until the last month when it trended high. There was a calibration performed right around the same time, which we think it caused it to deviate and trend upwards. The RSD for the probe was 0.86%. Like the other 2 probes, 99.9% of the time, it was within Denver Water's limits. It had an accuracy of just under 85%, which is probably due to it trending higher towards the end of the study. It also required no maintenance during the study.
Did it go?
Yeah.
Too early. Sorry, we'll fix our presentation here for a second. All right, so you got Rosemount, right? Your Yokogawa. Okay, so Yokogawa was the next one on our list. The Yokogawa performed pretty similarly to the rest. It was off to begin with. There was a little bit of a maintenance issue when we first started with the Yokogawa probe. Hence, you see the drift there in the beginning. It was off by about 0.2 when we first started off the probe. But then after our last calibration, after it had some time sitting in the water, the calibration, it came in line and held pretty well. The other thing is we noticed is like we didn't invalidate any of the maintenance data that's on this. So the blue spikes, typically you'll see those across all the graphs. Those were either like a power outage or some other maintenance done at a treatment plant that was standard across all of the probes, so that we didn't invalidate it since it was consistent amongst them all. Other than that, yeah, Yokogawa was 99.92% within limits, was 85.16% accurate, and the RSD was 1.51%. So that was one of the top 4 probes for that reason. Okay, on to Moffett. So, Moffett data, we'll go over the graphs here. It was only there for a 3-month period in time, and it was at a lower rate the whole time. I don't think it were over 20 MGD for that plant production. So there was lots of oscillations in there. So we kind of separated this data out so we can see the ranking a little bit better. Based on just Moffett data, it was ECD, SCAN, Yokogawa, and Chemtrack. So it changed the order up quite a bit. But as we go to the next graph here, you will see why. Okay, so there's ECD. So a lot of this was due to the low rate, right? They're running 20 MGD. It's not very well mixed at that point, and we were pulling it right at the DCB5 sample point. So it trended like this across all of the probes. It wasn't just one probe or the other. So based on that, our RSD was 1.5, percent within limits was 98.41%. pH range was 74.59% accurate. It was hard to read some of this data, right? We took it and did the same averaging across it. The green line there is your moving average of the benchtop probe. But because of the oscillations, there was lots of peaks and valleys that didn't necessarily meet up between the probes, so it was a little bit harder to get some of the data off of. Okay, so second one in line was SCAN. SCAN was reading pretty high in the beginning here, and then it had calibration. That was partially during the move, which you kind of see at the beginning here. I need a pointer. It started off reading pretty well with the plant probe and then started reading a little high. And then after our quarterly calibration, it came back and started reading in line pretty well. The standard deviation was 1.91%. Percent within limits was the 94.12. And then accuracy was 66.77. And Yokogawa. So Yokogawa was pretty consistent amongst the whole time there. It was just reading higher. You can still see all the same oscillations. Our RSD was 1.57%. And then percent within limits was 98.57, and accuracy was 61.37. So the accuracy was off because the peaks were a bit higher on the Yokogawa than the rest of the probes. And Chemtrack. So Chemtrack trended about the same. The data is pretty hard to read again. It's all kind of overlapping a little bit. Our RSD is 1.88%. Our percent within limits was 91.48, and our accuracy was 67.35. But overall, at least it was within the same bandwidth. But like I say, data was pretty hard to get any actual valid points out of it. All right, conclusion.
All right. So what we found was the ECD probe demonstrated the best performance out of the 11 probes tested. Several probes performed similarly to the ECD probe, but couldn't necessarily be distinguished from the others. And the best probes for Marston are ECD, Mettler-Toledo, Yokogawa, and Rosemount. We also determined that more work is needed on the North system to identify the most appropriate probe. There's an obvious difference in pH measurement between Marston and Moffett. And potential impacts on pH could include water quality or other seasonal variations that I will talk about on the next slide. Next steps. So we are going to continue with phase 2 pH pilot testing into the summer load season. As Alvin mentioned, Moffett was mainly running at 20 million gallons for the duration of the past 3 months. Once it gets up to 80 million gallons, we might see a deviation there. We also want to see what runoff does to the probes and how that impacts everything. And also seasonality can come into play, especially with water temperature. Marston was primarily spring, summer, and fall, while Moffett was in the winter. So temperature could be impacting that as well. We are also revisiting the Moffett pH A3 that was conducted in 2021. Presentations are going to be offered to the manufacturers, the treatment and water quality managers. We're also looking at getting the state and some other utilities and conferences on the books. Once again, we are going to be reconfirming instrument availability for procurement because in this day and age that changes on a daily basis. Supply chain issues are an ever-growing headache, so we definitely want to be aware of that and have the latest information when we're placing orders. We're also going to be developing an implementation plan to begin replacing the probes and start with compliance probes in the distribution system and treatment. So treatment NICS has 90,000 budgeted for 2023, which will get us about 20 units, and I have 50,000 for distribution to get us started. The rest are going to be systematically replaced over the next several years. Just as they fail, reach the end of their useful life. Useful life right now, we estimate between about 6 months to a year for a pH probe, and also the controllers that operate a lot of these probes are out of date and failing and no longer supported by the manufacturer. So the time is now to start replacing these probes. Also, it's more important than ever to keep the lead reduction program going. So these probes need to be replaced starting immediately. We are, where was I? We're also going to be installing new pH probes to standardize downstream distribution probes to the treatment plants. So what I mean with this is since every pH probe measures water in a different process differently, what we've been seeing out in the distribution system, the treatment plants might be putting out water a little bit low, and by the time it reaches the distribution system, it's a little bit higher. Both pH probes are technically still in range, but it still makes a lot of frustration and a lot of headaches and a lot of stress for everybody involved. So we're hoping by having the same manufacturer, we can see those values get a little bit closer and be more in line, which will give us a little more wiggle room to work with. And lastly, we're also going to be developing and implementing a communication and training plan. PR has been great for getting these up and running, as well as passing out our paper and coordinating with other utilities. And we're also going to be putting together a bunch of SOPs and working with manufacturers to provide training for the new technicians for all the new probes that we are going to be getting.
Cool. I think that's okay. So before we go on to comments, I'll actually go back. We kind of skipped over a little bit of the maintenance part of it, which Drake was kind enough to point out to us. That was a big reason we started doing this is, you know, the maintenance cost of what it's doing. I'm going to get back to the right slide here. Slowly but surely. All right, so this was the Moffett data, but the maintenance cost there on the right side. Oh, man. Wait for it. Thinking. I got a little too trigger happy apparently. Marston, there we go. Hopefully it stays there. Nope. Go back one. Oh, man. Sorry. It's a little slow than I'm used to. That's pretty bad. Wait for it. Oh, well, that's nice. This one. Okay, this cost came from. This was still a fairly short time for maintenance interval, right? This is less than a year. Most of the time, a brand new probe, you don't have a whole lot of maintenance in the first year. Half the probes that we tested actually were almost maintenance free in the year besides our calibration. Even according to manufacturers, the only thing they had on the list was basically cleaning. So that kind of reflects in here. All the numbers are fairly low. We're going to continue this into a phase 2. We're going to leave it at Moffett and let it run through a higher flow rates there at 80, 100 MGD at Moffett to see what it does. And we expect to see the maintenance costs go up a little bit on some of these probes. And we'll just kind of keep tracking it as we go across. We're still pulling this data But for now, I think we've got a pretty good conclusion of what we should at least do for some of the treatment plants. And hopefully it stays true for these top 4 probes throughout.
One other thing I want to point out, our current probe, Hawk, in this study, it cost us $340 to maintain, $340. And that was low compared to what we normally have seen in treatment. And another reason why I do this, and these probes we selected, $136. Big difference. So, big cost savings.
So do you want to put it into NTP, or are you going to do a separate study with NTP?
Repeat the question. There we go.
So basically the question was, are we going to use this data to pick a probe for NTP? And that's kind of a tough question. We don't know what NTP is going to be like. We expect it to be a little bit like Moffett because it's the same water that's coming down through the conduit, but we don't really know. So it's going to be determined, I guess. Once NTP is up and running, then we'll get some more data and see where it goes. Brandon?
But currently, the probes at NTP have already been selected and they're installed.
Yeah.
And if we have problems with them, then maybe the compliance will switch out. But we're gonna start with what they have. But we'll probably switch.
Don't know.
We will switch.
Yeah.
So following your presentations at ACE and all that, another water utility comes up to you and says, hey, I'd really like to try out the process that you guys had here, but what's the one thing that I should do first that you guys learned later on?
First thing we learned.
Repeat the question.
So
He gets it.
yeah, I guess trying to figure out a good way to reword the question, but what was the first thing that we learned that we would tell another water utility if they were trying to repeat the same study? The manufacturers were a big help. So I think overall, maybe we'd get them, like we started off with them, we asked them to donate it, right? And we kind of kept them involved in the whole time. But seeing that there's a bunch more options, right? We reached out to all the ones we could think of, we did some research. But as we were doing the study, more manufacturers came up with like, oh, we would have loved to be in there that we didn't think about. So maybe do a little bit broader reach when we start off with it. And we didn't know what to expect with the probes at all as far as the response goes. So you might have a different result than what Denver Water had with what we've seen based on your water.
Any question?
Yeah, as far as the technology that the probes were constructed with, did you guys notice nuances that made some of these perform better than others? I mean, I know fundamentally they typically all operate the same, but I'm just curious kind of if you noticed small things that made some of these maybe less maintenance or be more accurate compared to other models.
Okay, so the question was if we had noticed any nuances between the different types of probes, different manufacturers and the technologies that use, what the nuances we saw. And yeah, absolutely. Some of them responded way quicker, like typically one with the salt bridge, when we do a calibration, you do your calibration, it took a while before it would come back and read the temperature correctly, and you'd have to watch it for a while. There's some of the other ones that were gel filled with ceramic membrane. There's a vast variety out there, but they each had their own pluses and minuses, I would say. One thing we did notice is typically they responded a lot faster than what we're used to. I mean, these were obviously all brand new probes for the most part. So there are some actually that were donated to us that were actually used probes that they just replaced the membrane or whatever else on. But in general, they all responded pretty quick after a calibration, which was interesting to see because that's not typically what, at least we've seen with our current probes that are in the system.
Any more questions? Sir?
Educational question, how many total probes do we have?
11. So we tested 11. Or are you talking about just as far as Denver Water as a whole? Oh, what did we come up with the count was?
It's right around 300.
So the question was, how many probes does Denver Water have in the system? You said 300?
Yeah, it's close to 300.
Yeah. Between distribution and all the plants total, I think it's slightly under that, but. Yep.
I have a comment. So Brandon, good job on the disclaimer for the pilot study. Good job there. What I'd like to do is just commend this group for the amount of time and effort. You had 1,700 hours or 1,500 hours of time and effort in this pilot study. But I do want to point out the behind the scenes 24/7, 365 of monitoring and responding to these because they are tied to regulatory compliance. So Brandon and the team, thank you very much for your dedication. There was a lot of overtime and a lot of hours, weekend hours and after hours, that the team would go out and actually support and calibrate and make sure that those compliance probes were working properly. But I just wanted to give a shout out to the team for their dedication, so thank you.
Thanks.
Thank you for that. Yep.
I kind of have a two-parter here, maybe three.
Okay.
With the differences between the water quality from Moffett to Marston in the source water, and Moffett having lower conductivity and ionic concentration, did you learn that any certain probes are better equipped to handle those challenges of those concentrations being so low and the impact they might have had on the pH?
That one's all you. But yes.
So the question was, did we learn anything at Moffett from the low ionic strength water that they have up there? If any probes work better? Yes. So there are definitely probes that work better and can handle that lower ionic strength water, which is great news. I was really excited to see that. Still continuing on, because again, conductivity is going to change through runoff, so we really want to see how that gauges. But yeah, we have some promising leads.
That's great news. Does that concern you at all then to potentially have two different probes in north and south system? Just like you were talking about the difference in probes between treatment and distribution?
So question was, does it concern us having more than one brand of pH probe in the system between north system and south system and distribution? Not really. Just looking at the results of the study, everything lines up fairly well with each other. And again, one of the main goals and conclusions of this study was to align treatment plants with their downstream sensors respectively. So that way, if there are some nuances and one brand of pH probe reads the water lower than the higher one, hopefully by aligning those, we can see those variances come a lot tighter. So not really a concern, no.
And to add on to that, we selected 4 probes, and we selected this on purpose. It wasn't to select the number 1 probe. We didn't want all our eggs in one basket.
Yes.
These 4 that the team selected, or the study actually selected for us, right? They all work well together, and we're confident in them, but we don't want all our eggs in one basket. I'll take, for example, Rosemont. If I was to order one of those right now, I'm not going to get it for a year. You know, we can't have that, you know, the supply chain issues. So, you know, another manufacturer could get it to us in 6 weeks. So we want to make sure we get into these supply chain issues. We had a little bit of a scare, 6 months ago with our current pH probes and getting the supplies we needed to maintain them all. And it came very close to, we weren't going to be able to do that. So we want to make sure we're diversified that way. Does that make sense? That's why we went with 4.
Part 3?
Part 3, are you considering any other statistical analyses or tests to look at difference from the mean or variation between the different probes?
I guess
Yeah.
the question was, statistically, are we going to look at this in a different way? We were considering running an ANOVA to look at the data, but yeah, there's definitely a lot out there that we can still visit.
Well, that'd be fun.
And the nice part is, right, we have all this raw data saved from everything without any evaluation. We have all the raw data. So if we do want to go through and try it a different way and be like, hey, what else are the results we're going to get? It's an option to do. And that's partially why I want to continue on with Moffett and just add all that data to it and see what it comes out, average it even longer.
Back row.
So you've done a study, you had 11 probes. One of the first things that you learned in the study was the fact that there's more than 11 out there. Are you considering continuing the study and adding new probes in at some point in the future possibly?
All right, so the question was, there's 11 probes that we selected on this. There's obviously a lot more out there. Are we going to plan on adding more to it and continuing on? At this point, I don't think for us there's a benefit too much in it, right? We've already spent a kind of a decent amount of time working on this. I think we've got pretty good options for what it is. And as things go on, right, the technology is going to change. Like he said, it's just a snapshot of what we had available at that time that we reached out to. And, you know, for other manufacturers, all the probes were donated to us for this. So maybe what we do with that board later on after we're done with the phase 2 with Moffett, maybe we can loan it to another water utility and see what they do, or they can add their own to it. So we'll kind of see where that goes. It's kind of open-ended right now.
But when you think about our reason for action, we solved our reason for action on why we're doing this. We have a probe that now meets our needs. So if we find in a year or two these probes not meeting our needs, maybe. But at this point, we don't see the need. Any more questions? Alfonso.
Given your differences in water quality, north and south systems, and what you guys are showing here, there's a pH probe that might read better specific to type of water quality. How does that translate to like your blending zones in the distribution system where, obviously I don't think you guys have an answer, but it's something you guys are just about here?
Brandon, your distribution.
Yeah, I'll take that one. So the question was, with the different probes behaving differently in our two sources, do we have any concerns, or are we aware about the blending zones that we see in the distribution system? What's going to happen at those sites? Yeah, definitely aware of that. That is going to be part of the implementation plan, and that is why we are continuing Moffett as well, so we can be absolutely sure of the probes that we select there. But yeah, I think the low ionic strength water out at Moffett is probably one of the biggest things right now, and we definitely want to make sure that the probes that we select in the mixing zones will work for both north and south systems. Absolutely.
Add to that question, is there any, I guess, based on these results, is Moffett considering any optimization on the treatment side to better align with the south system?
The question was, is Moffett considering any optimization to align more with the south system? As far as I know, yes, that is part of the Moffett A3 that's being done right now. So we're looking into everything. Yeah. Yep.
Alfonso.
Alfonso?
Can you clarify something for me? Your probes that you are comparing these probes here to, is that the same probe as your compliance analyzer, or is this your benchtop probe? Is that the compliance probe, or is it a different probe that you're comparing these to?
The one Moffett was a hot probe, I believe.
Okay, so yeah, and the question is on our graph here, our green line, our benchtop probe, what probe was that, and how the comparison is. So in the report, it actually shows the actual model number of it is, but it's the typical benchtop probe that the plants use now, which is a Hawk probe. It's at a 281, I believe, right? Anyways, it is a current Hawk benchtop probe. We didn't want to change that because we were already using that across the plants for a standardized measurement. We've never really had any problem with the accuracy of that when it's done correctly. So we did leave that as the benchtop probe, and that was the same between both the plants.
Are you assessing accuracy of that one by just routine calibration or something?
Yeah, so the benchtop probe was calibrated basically every shift, so every 12 hours. They did a calibration on that to verify that the benchtop probe was accurate. So that was our best, guess, right? Like, we took all the preventative steps we could of doing the calibration, checking everything ahead of time, doing that twice a day.
Phil.
Yeah, are you gonna prioritize the probe for the distribution system as far as placement cycle, and how long do you think it's gonna take?
You want me to handle this? So the way we're going to handle, well, the question was how we're going to prioritize and what probes are we going to pick this year to replace? And as Brandon mentioned before, we're going to replace about 20 in treatment, and Yours is probably about 15 with the amount of money, current money budgeted for it. We're going to reach out to, we're reached out to the treatment plant managers to have, we gave them our recommendations, and they just signed off on that. And Brandon's going to reach out to your team and the other teams with his recommendations, and then you guys will have some input, and we'll go with that, because I'm sure you have your top ones you would like replaced, you know. Does that answer that question, Phil?
Yes.
Thank you. Any other questions? Sir?
The RST value, is that the standard deviation value closest to like accuracy to the results?
James?
What was the question? Sorry.
What is the RST value of
It's the spread relative to the mean of the plant probe that we used.
Thank you.
Great questions. Any more great questions? All right, well, thank you all for coming. Thanks for being part of this. I got some printouts, 38 pages. Those are the reports. If you want all the scientific data and like that, that's right here. We have some for you. And we also have it available electronically. This was also recorded. It's going to be on Inflow probably this afternoon. And that way people that couldn't make it today, working graves and stuff like that, they could watch this. So make sure you go back and let your teams know it's there if they want to see it. And we're here if you ever have any more questions. And thanks for coming.
Thank you.